Hello, my name is Tristan Pete, and this is my presentation for Lab 2 in Physics 2212 at Georgia Tech. The objective of this lab is to build on our understanding of charge and its role in everyday objects by creating a more sophisticated model. What has changed since Lab 1? The main difference is we're now going to treat the charge as a line of charge rather than just a point charge. And this enables a more accurate calculation for the charge of the tape and a realistic representation of the charge tapes. In the end, the positively charged tapes, when modeled as lines of charge, have a charge of approximately 4.728 times 10 to the negative 8 coulombs. We are making a few key assumptions, and the first one is that the force of gravity and the electric force are the only forces playing on tape B when suspended between the two books, so that is, we're ignoring air resistance. We're also assuming that the U tapes have the same amount of charge and that the charge is evenly distributed on both tapes. Just to review some of the main concepts from Lab 1, we are using Newton's second and third law. And Newton's second law helps us find the force of gravity, which is mass times acceleration. And Newton's third law dictates that it is equal to the electric force, which can be seen on the right when you see tape B has two forces acting upon it, and they're equal but opposite when in equilibrium. We're also going to use the Coulomb force, which governs the interactions between 2 point charges. The procedure from Lab 2 was to create two charge tapes by ripping them off of one another, suspending one charged piece of tape between two books, and then bringing the other tape near to determine the distance when it began to levitate. The distance I calculated was 0.0025 meters, and the estimated magnitude of the charge on one tape was 1.68 times 10 to the negative 9 coulombs. The equation that we manipulated to find this can be seen in the bottom left corner, and the model of this interaction can be shown on the right. The yellow arrows were representative of the electric field force, and the orange arrow is the gravitational force. So when we build our new model, we're going to split the charge evenly across the length of the tape, split the tape into n pieces so the charge on each tape is dq equals q over n, and increase n until the accuracy of the model increases. So effectively, we're using integration to find the charge of the entire tape. The model on the bottom shows many arrows for the electric field instead of just one for a single point charge. The magnitude of Fe calculated by the lines of point charge was 4.8 times 10 to the negative 5 newtons when the number of point charges or electric forces considered was 10,000. Again, this is just a reminder of the equation we're using here. The reminder of the charge, the magnitude of the charge on the tape that we calculated for the lines of point charge was 4.7 times 10 to the negative 8 coulombs when the number of point charges or electric fields we were considering was 10,000. This shows the improvement of the model from point charges used in Lab 1, and then there's 10 arrows or 10 charges on the tape on the middle picture, and then 50 in the bottom right picture. The tape B is modeled by the red balls in the two rightmost pictures, and tape A is modeled by the blue balls. The electric field is the green arrows, and the electric force is the white arrows. Here's a snippet of the code that I wrote, and what it really is doing is iterating through all of the charges on the tape and calculating an electric field for it, and then summating it in the bottom, and then creating two arrows for the electric field and the electric force. The picture on the right is when the number of charges on the tape is 10,000, and the resulting calculations is also shown. So a few critical questions. What if we modeled each of the tapes as a single point charge, like in the previous lab, and then compare this value to what we used for our line charge model? Why do these estimates differ, and which one's more likely closer to the real value of line? So the magnitude of the electric field that we calculated for the point charge, which was Lab 1, was 1.962 times 10 to the negative 3. And it had a total charge on the tape of negative 1.68 times 10 to the negative 9 coulombs. You can also see the progression of how these numbers change from right to left as we increase n. And what we're doing really here is increasing accuracy of a real-life model. Really, there could be Avogadro's number charges here, but 10,000 is the closest that I could do with my computer power, and I calculated 4.839 times 10 to the negative 5th as the magnitude of the electric field in newtons, and negative 4.728 728 times 10 to the negative 8 as the total charge on the tape in coulombs. Thank you for watching.